November 12, 1942, Richmond, California. The sparks cascading from 2,000 welding torches illuminated the interior of Permanente Metals Corporation's Yard No. 2, like an electrical storm contained beneath a single roof. The air tasted of scorched metal and ozone. Each arc of electricity joining steel to steel represented a direct violation of maritime tradition, stretching back 3,000 years. British Admiralty had forbidden this exact process on warship hulls. Lloyd's of London, the institution that determined whether ships were insurable, had declared welded construction insufficiently proven. The American Bureau of Shipping had required special exemptions. Yet here, in this massive facility carved from California mudflats just 18 months earlier, over 1,000 workers were assembling a complete 441-foot cargo vessel using a technique that traditional shipbuilders considered somewhere between reckless and impossible. The ship rising on Building Way 7 was the SS Robert E. Peary. It had existed as separate components just 4 days earlier. Now, through 60,000 individual electric arc welds performed by workers who had learned their craft mere weeks before, it stood complete, ready to slide into San Francisco Bay, ready to prove that everything the maritime establishment believed about proper ship construction was wrong. The transformation that made this moment possible had begun not in a shipyard, but in the dusty canyons of the American West, where a technique dismissed by centuries of nautical tradition would find its unlikely champion. The story of how one forbidden welding process made Liberty ships appear in days instead of months is ultimately a story about the collision between craft tradition and industrial necessity, about how the very thing authorities prohibited became the innovation that saved democracy. December 27, 1940. New York City offices of Todd Bath, Iron Works, Henry J. Kaiser, a 58-year-old construction magnate who had never built a ship, never managed a shipyard, and had spent his career moving earth and pouring concrete across the American West, signed his first shipbuilding contract. The Todd executives watched with barely concealed skepticism. Kaiser had promised to deliver 30 cargo vessels for the British government within 2 years. Traditional shipyards required 6 to 8 months to build a single vessel of that class. Mathematics seemed impossible. What the Todd executives didn't know, what the United States Maritime Commission didn't know, what the British Admiralty officials ordering these ships didn't know, was that Kaiser carried with him experience in a technology that traditional maritime engineers considered inappropriate for ship construction. He had mastered electric arc welding building oil pipelines across the western deserts. He had joined massive sections of steel pipe using portable generators and arc welders in locations hundreds of miles from civilization. The technique was simple in principle. An electric current flowing between a steel electrode and the base metal created temperatures exceeding 3,500 degrees Fahrenheit. The intense heat melted both the electrode and the base metal, fusing them into a single joint stronger than either piece alone. The process required no complex machinery, no teams of skilled craftsmen, no months of apprenticeship, just electricity, a welding rod, and approximately 2 weeks of training. This was precisely why traditional shipbuilders dismissed it. Ships were serious business, they argued. Lives depended on hull integrity. Ocean conditions demanded construction methods proven through centuries. Welding lacked that proof. The British Royal Navy had issued explicit regulations in 1938. Welding is not permitted on warship hulls. The risk of hidden defects and unpredictable failure modes makes welded construction unsuitable for vessels operating in combat conditions or severe maritime environments. Lloyd's of London, the institution whose approval determined whether ships could be insured, and therefore whether they could operate commercially, maintained similar restrictions. Welded cargo vessels required special inspection protocols, higher insurance rates, additional structural requirements. The message was clear. Riveting represented proven technology. Welding represented uncertain risk. Yet the mathematics of shipbuilding in 1940 pointed toward a different conclusion. A traditional riveted cargo ship required approximately 1 million rivets. Each rivet needed to be heated in a forge, carried to the joint site while still hot, held in position by one worker, and hammered into place by another. A skilled four-man riveting crew working with perfect coordination could install perhaps 100 rivets per day. The calculation was straightforward. 1 million rivets divided by 100 rivets per day equals 10,000 worker-days. Assuming 3 riveting crews working simultaneously, a single ship required more than 3,000 days of riveting work alone before accounting for all other construction tasks. Electric arc welding changed this calculation fundamentally. A single trained welder could deposit 4 feet of weld per hour. A Liberty ship required approximately 50 miles of welding. Assuming 8-hour work days and accounting for preparation time, a crew of welders could complete all welding on a single ship in approximately 1,000 worker hours. The efficiency gain was nearly tenfold, but efficiency mattered little if welded ships failed at sea, and the traditional maritime establishment possessed 3,000 years of evidence that riveted construction worked. Kaiser possessed enthusiasm and pipeline experience. The first test came in early 1941, when Kaiser's newly constructed Richmond Yard No. 1 began, building 30 ocean-class cargo ships for Britain. These vessels, based on an obsolete British tramp steamer design from the 1890s, would be built entirely using electric arc welding. The Maritime Commission engineers who visited the facility in its early stages filed reports that captured their deep concern. Vice Admiral Emory Land, chairman of the United States Maritime Commission, examined the welding specifications with visible skepticism. His private correspondence, preserved in the National Archives, revealed the establishment's perspective. Kaiser proposes to build ocean-going cargo vessels using all-welded construction. Welding has never been proven at this scale. The British Navy explicitly forbids welded warship hulls. German experience with welded pocket battleships showed weight savings but raised questions about long-term durability. Kaiser claims pipeline welding experience translates to maritime construction. This assumption is unproven and potentially dangerous. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The technical objections to welding went beyond mere traditionalism. They reflected genuine engineering concerns rooted in material science that 1940-era metallurgists only partially understood. Steel behaves differently under different conditions. Temperature matters. Stress concentration matters. The way forces distribute through joined materials matters. Riveted construction had one crucial advantage that welding lacked. When a crack formed in a riveted ship's hull, it propagated until it reached a rivet line. The crack couldn't continue through the overlapping plates that riveting required. The joint itself acted as a crack arrestor. The damage remained localized. The ship stayed afloat. Welded construction eliminated this safety feature. 2 steel plates joined by welding became effectively one continuous piece of metal. A crack forming anywhere could propagate indefinitely. If the steel's properties allowed brittle fracture, a welded ship could theoretically crack completely in half. This wasn't theoretical paranoia. German engineers building the pocket battleships Deutschland, Admiral Scheer, and Admiral Graf Spee in the 1930s had chosen extensive welding specifically to save weight. Treaty of Versailles restrictions limited these ships to 10,000 tons displacement. Welding saved approximately 1,000 tons compared to riveting, allowing heavier armament within treaty limits. But reports filtering back from German naval operations suggested durability concerns. Cracks appeared at weld points under sustained stress. Repairs required specialized equipment and highly trained welders unavailable in most ports. The British Admiralty, analyzing this experience, concluded that welding's weight savings came with unacceptable risks for combat vessels, hence the prohibition. Yet Vice Admiral Land faced a problem that made risk calculations different. German U-boats and surface raiders were sinking Allied merchant shipping faster than traditional shipyards could replace vessels. In 1941 alone, approximately 3.6 million tons of Allied shipping would go to the ocean floor. Britain was literally starving. American shipyards using conventional riveting methods would require an average of 230 days to build a single cargo ship. At that pace, the Allies would lose the Battle of the Atlantic before American industrial capacity could respond. The decision to approve Kaiser's welding approach represented not confidence in the technology, but desperate necessity. The approval came with conditions. Kaiser would implement rigorous welding standards. Every weld would be inspected. Workers would complete formal training programs. Quality control would exceed standards for riveted construction. The Maritime Commission would monitor production closely and halt the program if welded ships showed structural problems. Kaiser agreed to these terms, though he privately considered most of them unnecessary. He had been welding steel for 2 decades. Pipelines carrying high-pressure fluids across temperature extremes, suspension bridge cables supporting millions of pounds, concrete forms bearing massive loads. Welding worked. The question wasn't whether welding was safe. The question was whether shipbuilders would adapt fast enough. The Richmond Yard No. 1 rose from empty mudflats between January and December 1941. Traditional maritime engineers visiting the site were horrified by what they saw. Instead of the enclosed building ways and overhead gantry cranes that characterized proper shipyards, Kaiser had constructed what looked like an oversized automotive assembly plant. 7 parallel building ways ran the length of the facility. Railroad tracks crisscrossed the yard, designed to move massive prefabricated steel sections. Open areas designated for sub-assembly surrounded the building ways. The entire layout prioritized rapid welding of large components over the careful piece-by-piece construction that traditional builders practiced. John Riley, chief naval architect for Bethlehem Steel Corporation and a 30-year veteran of shipbuilding, submitted an inspection report in May 1941 that was marked confidential at the time. His assessment mixed technical criticism with grudging respect. Kaiser's facility violates every principle of efficient shipyard organization established through decades of experience. His building ways are too short. His prefabrication areas consume excessive space. His dependence on welding creates quality control challenges that riveting avoids. Yet the facility is clearly designed for what Kaiser claims: rapid assembly of prefabricated sections. If welding proves viable at maritime scale, this approach could succeed. That remains a savant-to-cyberface, substantial if. The arrival of workers provided the next phase of Kaiser's revolution. Traditional shipyards recruited from established maritime communities, skills passed from father to son across generations. A proper shipfitter served 4 years as apprentice, 4 more as journeyman, and 10 total before master craftsman status. Kaiser advertised in newspapers nationwide. Help wanted, shipyard workers, no experience necessary, training provided, wages 20% above standard industrial rates. The first groups arrived in Richmond in August 1941. Former secretaries, farmers, retail clerks, housewives, men beyond draft age, women whose husbands had enlisted, people who had never seen an ocean, much less built a ship. Kaiser's training schools taught them one skill: welding. Not comprehensive shipbuilding knowledge, not traditional maritime crafts, just welding. How to strike an arc, how to maintain proper electrode angle, how to control heat and travel speed, how to recognize good welds from bad. The training lasted approximately 2 weeks for basic proficiency. Some workers mastered simple welding positions in as few as 10 days. Others required 3 weeks to handle more complex overhead or vertical welds. All of them would have been laughed out of traditional shipyards. A proper ship welder requires 4 years of apprenticeship, minimum, the old builders insisted. Kaiser's people are performing industrial assembly, not maritime craftsmanship. This was precisely the point. Kaiser wasn't trying to train traditional ship welders. He was creating specialized assembly line workers who would perform specific repetitive tasks. One worker welded vertical seams on bulkheads, another welded horizontal deck plate, a third specialized in curved hull sections. Each person mastered one operation and did it hundreds of times. The approach borrowed directly from automotive manufacturing, where complex products were assembled from simple repeated operations. Traditional shipbuilders found this concept offensive. Ships weren't automobiles. Maritime construction demanded comprehensive understanding. Workers needed to grasp how their specific task related to overall vessel integrity. Specialization created ignorance. Ignorance created danger. Kaiser's response was characteristically blunt. Results matter. Training time matters. Production numbers matter. His welders didn't need to understand ship design. They needed to create consistent, high-quality welds at specific locations following documented procedures. Engineers handled design. Inspectors verified quality. Workers executed their assigned tasks. The system was designed for scale, not tradition. The first ships, completed in late 1941 and early 1942, provided the critical test. Would vessels built entirely by arc welding and assembled by inexperienced workers hold together at sea? The British crews receiving these first ocean-class ships approached them with deep suspicion. Hastily built American cargo vessels constructed using forbidden welding techniques by untrained workers. The ships looked crude. Welding beads showed clearly on the hulls. The vessels lacked the smooth finish of traditionally riveted ships. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel. British maritime officials conducted thorough inspections before accepting delivery. They examined welds with particular scrutiny, searching for the defects that welding's critics had predicted. Cracks, porosity, incomplete penetration, slag inclusions, structural weaknesses waiting to fail under storm conditions or combat stress. To their surprise, most welds passed inspection. Kaiser's rigid quality control, implemented under Maritime Commission oversight, had worked. The welds were crude but functional, ugly but strong. The ships were commissioned and departed for Atlantic convoy duty. Months passed. The ocean provided the ultimate test. North Atlantic storms in winter subjected ships to forces that no dockside inspection could simulate. Waves 50 feet high, sustained winds exceeding 60 miles per hour, sub-zero temperatures, the constant flexing and stress that revealed hidden weaknesses. And the ships held together. They weren't elegant. They weren't comfortable. British crews complained about cramped quarters, inadequate heating, and a dozen other shortcomings. But the welded hulls remained intact. The forbidden technique worked. The validation of welded construction at sea created momentum that traditional builders couldn't stop. By spring 1942, the United States Maritime Commission was receiving reports from convoy operations that contradicted decades of maritime wisdom. Welded ships built by inexperienced workers in hastily constructed yards were performing as well as traditionally riveted vessels built in established facilities. The implications were staggering. If welding actually worked, if training time could be reduced from years to weeks, if ships could be assembled from prefabricated sections rather than built piece by piece, then production capacity was limited only by industrial will and raw materials. The question was no longer whether welding was acceptable. The question became how fast welding could scale. Kaiser's Richmond yards provided the answer. Production accelerated through late 1941 and early 1942 in ways that seemed impossible to observers familiar with traditional shipbuilding pace. The first ocean-class ship had required 197 days from keel laying to delivery. Ship number 2 required 169 days. Ship number 5 required 128 days. Ship number 10 required 97 days. The improvement curve was steep and consistent. Each ship built taught lessons that accelerated the next. Welders became faster, through repetition. Engineers identified bottlenecks and eliminated them. Supervisors refined procedures. Suppliers learned to deliver components on predictable schedules. The entire system was optimizing itself through experience. By February 1942, the Richmond yards had transitioned from building ocean-class ships for Britain to building Liberty ships for the American merchant fleet. The Liberty ship design, formerly designated EC-2SC-1 for emergency cargo, represented the Maritime Commission's standardized vessel optimized specifically for mass production using welding. The Liberty ship was deliberately simple. A basic cargo hull, 441 feet long and 57 feet wide. 5 cargo holds provide 564,000 cubic feet of space. A triple expansion steam engine producing 2,500 horsepower. Design speed of 11 knots, adequate for convoy operations, but nothing impressive by maritime standards. Every aspect of the Liberty ship design prioritized manufacturability over performance. The hull used simple flat and gently curved plates that could be cut and welded quickly. The superstructure mounted amidships in a standard configuration. The engine was antiquated but reliable and easy to produce using existing foundry capabilities. Even the armament was standardized. 1 3-inch gun aft, 1 5-inch gun forward, 8 20mm anti-aircraft guns. William Francis Gibbs, America's most respected naval architect, had created the Liberty ship plans based on British designs. His firm Gibbs and Cox had designed more ships than existed in many nations' entire fleets. Gibbs possessed formal training, decades of experience, and a perfectionist's attention to detail. He initially opposed welded construction on principle. Ships should be built to last generations, Gibbs argued. Welding creates stress concentrations. Riveting provides redundancy through overlapping plates. Speed of construction matters far less than longevity and reliability. These objections were technically sound but strategically irrelevant. The war wouldn't wait for perfect ships. The war needed adequate ships immediately. Gibbs adapted his designs for welded construction under protest, incorporating features meant to mitigate welding's perceived weaknesses. Thicker plates at stress points, rounded corners on cargo hatch openings to reduce stress concentration, additional structural reinforcement where welded seams intersected. The Liberty ship reflected a compromise between traditional engineering standards and emergency production requirements. What Gibbs and other traditional engineers failed to anticipate was how quickly Kaiser's workers would master welding at production scale. The Richmond yards employed over 10,000 workers by spring 1942. Most had been welding for less than 6 months, yet they were producing welds that consistently passed inspection. The secret wasn't individual skill. The secret was systematic process control. Kaiser's engineers had broken welding down into specific procedures with documented parameters. Electrode angle, arc length, travel speed, heat input, bead pattern. Every variable was specified. Every welder followed the same procedures. Every weld was inspected using the same criteria. This standardization allowed rapid quality assurance. Inspectors didn't need to evaluate each welder's overall craftsmanship. They needed to verify that specific procedures had been followed and that the resulting weld met measurable standards. Visual inspection checked for cracks and porosity. Radiographic inspection on critical welds revealed internal defects. Destructive testing of sample welds validated procedures. The approach was fundamentally different from traditional maritime practice. Craft guilds had always relied on master craftsmen whose judgment determined quality. Kaiser relied on documented procedures and measurable standards. The difference was profound. Judgment requires years to develop. Procedures required weeks to learn. Albert Wooding, production supervisor at Richmond Yard No. 2, explained the philosophy in a 1943 interview with Fortune magazine. Traditional shipbuilding depends on craftsmen who understand the complete vessel. Our approach depends on workers who execute specific operations correctly. A traditional shipfitter needs 10 years of experience to make good decisions. Our workers need 2 weeks of training to follow good procedures. The procedures encode the experience. The workers execute the procedures. This industrial philosophy extended beyond welding to every aspect of ship construction. Hull sections were fabricated in dedicated areas where jigs and fixtures ensured consistent dimensions. Bulkheads were welded in dedicated stations. Deck houses were completely outfitted before installation. Engine rooms were assembled as modules. The prefabrication strategy allowed parallel production that traditional sequential building couldn't match. While one crew welded hull plates in the main assembly area, other crews built bow sections, stern sections, deck houses, and engine mounts simultaneously. When all components reached completion, massive cranes lifted them into position, where welding crews joined them together. A conventional shipyard built ships from keel to deck in sequence. Each operation waited for the previous operation to complete. Kaiser's yards built ships from components to assembly in parallel. Multiple operations progressed simultaneously across different areas. The total construction time depended on the slowest component, not the sum of all operations. By summer 1942, average Liberty ship construction time at Richmond had fallen to 70 days. Some ships were completed in under 60 days. The yards were delivering cargo vessels faster than German U-boats could sink them. The mathematics of attrition had reversed. American production capacity was overwhelming Axis interdiction capability. But mathematical victory wasn't the same as technical perfection. The welded Liberty ships, built so quickly by workers so inexperienced, carried hidden vulnerabilities that traditional shipbuilders had warned about. The warnings were about to be vindicated in the most dramatic way possible. January 16, 1943. Swan Island Shipyard, Portland, Oregon. The SS Schenectady, a T-2 tanker built using the same welded construction methods as Liberty ships, sat moored at the fitting-out dock. The vessel had been completed just days earlier and was undergoing final preparations before entering service. At 10:30 p.m., an explosive boom shattered the cold night. Workers rushed to the dock and discovered that the Schenectady had cracked completely in half. The ship's deck and side shells had fractured from gunwale to gunwale. Only the bottom plates held the fore and aft sections together, preventing the ship from separating entirely. The failure was catastrophic and completely unexpected. Schenectady hadn't been at sea, hadn't encountered storm conditions, hadn't sustained combat damage. The ship had simply fractured while sitting peacefully at dock in relatively mild weather. The crack ran straight through welded seams and base metal alike. Everything Kaiser's critics had warned about seemed confirmed. Within weeks, similar failures appeared across the Liberty ship fleet. The SS John P. Gaines cracked in half in the North Pacific in July 1943, less than 6 months after construction. The bow presumably sank. The stern drifted ashore in Alaska. 10 crew members were lost. The SS Esso Manhattan suffered complete structural failure. The SS Poneganyset split apart. By mid-1943, approximately 1,500 instances of significant cracking had been documented across the Liberty ship fleet. 3 ships had broken completely in two. The catastrophic failure rate was small, approximately 0.1% of production. But even one ship cracking in half at sea was unacceptable. The Maritime Commission convened emergency investigative committees. Naval Research Laboratory metallurgists examined failed sections. British Admiralty assigned Constance Tipper, one of the first women to study natural sciences at Cambridge University, to lead parallel investigations. The question was urgent and technically complex. Why were welded ships failing? The investigations revealed that welding itself wasn't the primary problem. The failures resulted from a combination of factors that welding made more dangerous, but didn't create alone. The first factor was steel quality. Liberty ships used semi-killed steel, a grade adequate for riveted construction but prone to brittle fracture at low temperatures. Steel behaves differently at different temperatures. At warm temperatures, steel deforms plastically when stressed. The material stretches and bends before breaking. At cold temperatures, steel transitions to brittle behavior. The material cracks suddenly without warning. The transition temperature varies by steel composition and processing. Liberty ship steel had ductile to brittle transition temperatures around 40 degrees Fahrenheit. North Atlantic waters in winter hovered near 32 degrees Fahrenheit. The steel in Liberty ship hulls was operating in its brittle regime. A crack forming under these conditions could propagate catastrophically instead of being arrested by plastic deformation. The second factor was stress concentration. Liberty ship designers had specified square corners on cargo hatch openings. Square corners create stress concentration points where forces multiply. Under normal conditions, properly designed structures handle these stress concentrations. But combined with brittle steel at low temperatures, stress concentrations became crack initiation sites. The third factor was weld quality. Not all welds, but some welds. Hydrogen embrittlement from damp electrodes, slag inclusions from rushed work, lack of fusion in poorly executed passes. Most Liberty ship welds were acceptable, but some contained defects that became crack starting points. The fourth and critical factor was that welding eliminated crack arresters. A crack forming in a riveted ship stopped at rivet lines. A crack forming in a welded ship could propagate indefinitely through continuous metal. If the crack started at a stress concentration, in brittle steel, at low temperature, and the weld contained defects, catastrophic failure became possible. The solution required changes across multiple dimensions. The Maritime Commission revised specifications to require killed steel with improved fracture toughness. Liberty ship designers rounded cargo hatch corners to eliminate stress concentrations. Kaiser's yards installed crack-arresting devices called crack arresters or gunwale bars at strategic locations. These were riveted or especially strong welded seams designed to stop propagating cracks. Welding procedures were tightened. Electrode storage became climate-controlled to prevent moisture absorption. Inspection frequency increased. Welders whose work consistently showed defects received additional training or reassignment. The changes worked. No ship equipped with crack arresters ever suffered catastrophic failure in service. The brittle fracture problem, while never completely eliminated, became manageable. The crisis validated both welding's critics and its defenders. Critics had been right that welding created risks that riveting didn't. Defenders had been right that welding problems could be solved through engineering analysis and process improvement. The ultimate lesson was that new technologies reveal unexpected challenges that must be addressed systematically rather than abandoned reflexively. Through this crisis, production continued. The Richmond yards maintained their accelerating pace. By fall 1942, Liberty ships were being completed in under 50 days on average. Competition had developed among Kaiser's 7 yards spread across California, Oregon, and Washington. Edgar Kaiser, Henry's son and vice president overseeing all Kaiser shipyards, managed the Oregon facilities. Clay Bedford oversaw Richmond. The two men began an informal contest to see whose facility could build ships faster. The Oregon Shipbuilding Corporation built the Joseph N. Teal in just 10 days in September 1942. The achievement was extraordinary. A complete Liberty ship assembled from keel laying to launch in 240 hours. Vice Admiral Emory Land, visiting Richmond shortly after, made an offhand comment to journalists that Clay Bedford overheard. The Admiral remarked that Liberty ship construction had improved remarkably, but noted that even the recent speed record seemed modest compared to what mass production had achieved in other industries. Bedford interpreted the comment as a challenge. He proposed to Vice Admiral Land that Richmond Yard No. 2 would attempt to build a complete Liberty ship from keel laying to launch in under 5 days, half of Joseph Teal's record. Land, skeptical but intrigued, authorized the attempt with one condition. It must not disrupt regular production schedules. The yards were delivering ships for actual combat operations. Publicity stunts couldn't interfere with military necessity. Bedford accepted the terms and selected the 47th hull to be built at Yard No. 2 for the record attempt. The ship would be named SS Robert E. Peary, after the Arctic explorer. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Peary construction represented prefabrication strategy reaching its ultimate expression. Every major component was built, inspected, and staged before the keel touched the building. The bow section, comprising more than 50 individual pieces, had been fully welded and equipped with anchor hardware, chain lockers, and forward crew quarters. The stern section included completed steering gear, propeller shaft, and aft crew spaces. 4 complete cargo holds, each a massive rectangular structure of steel, waited to be lifted into position. The engine, a 140-ton triple-expansion steam power plant built by Joshua Hendy Ironworks in Sunnyvale, had been mounted on its foundation structure and tested before leaving the factory. The deckhouse was completely outfitted down to bunks and electrical fixtures. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel. Starting Sunday, November 8th, at 1 minute past midnight, over 1,000 workers operating in carefully coordinated shifts would attempt something unprecedented in maritime history. The building was cleared, cranes were positioned, component staging areas were organized for optimal flow. Every worker knew their specific task and sequence. The keel was laid at 12:01 a.m. By sunrise, the bottom plates were welded in place. By Monday afternoon, the bow and stern sections had been lifted by massive cranes and welded to the hull. The 4 cargo holds dropped into position Tuesday morning. The engine installation, typically requiring 3 weeks in traditional shipyards, took 8 hours using cranes to lower the complete pre-assembled power plant into the prepared engine room. The welding pace was relentless. 17 banks of welding machines on each side of the hull. Pre-assembled deck sections lowered into place and welded in just hours. The deckhouse, complete in every detail, positioned and secured by Wednesday. By Thursday morning, November 12th, just 4 days after the keel touched the building way, the SS WWII, Peary stood completely. At 3:30 p.m. on Thursday, November 12th, after 4 days, 15 hours, and 29 minutes of construction, the WWII Peary slid down the launching rails into San Francisco Bay. The crowd of observers included maritime officials, military officers, competing shipyard owners, and journalists from across America. Many had arrived expecting to witness either failure or a compromised vessel that looked complete but lacked functionality. What they saw instead was a fully operational Liberty ship that required only minor fitting out before entering service. The ship was delivered for actual service on November 15th, setting an additional record of 7 days, 14 hours, and 32 minutes from keel laying to full delivery. Vice Admiral Land, present for the launching, made brief remarks recorded by newsreel cameras. His words captured the maritime establishment's forced recognition that everything had changed. 6 months ago, I would have called this impossible. Traditional shipbuilding wisdom accumulated over 3,000 years said you cannot build a proper ship in 5 days. Henry Kaiser has made traditional wisdom obsolete. The United States Maritime Commission will now require all contracted shipyards to adopt these methods. The psychological impact on traditional shipbuilders was profound and immediate. The same yards that had dismissed Kaiser as an ignorant outsider just 18 months earlier now sent engineers to study his approaches. The president of New York Shipbuilding Corporation, one of America's oldest and most prestigious yards, visited Richmond in December 1942. His confidential report to his board of directors revealed complete ideological collapse. Kaiser has achieved what our industry considered impossible by refusing to accept our limitations. He treated shipbuilding as a manufacturing problem rather than a craft tradition. He simplified where we sought perfection. He standardized where we customized. He trained masses of unskilled workers where we cultivated generational expertise. The result is ships built in 1/10 the time at 2/3 the cost. We must either adopt his approaches or accept irrelevance. By early 1943, Kaiser's influence had transformed American maritime production. 18 shipyards across the country were building Liberty ships using prefabrication and welding. Average construction time had fallen from 230 days initially to just 42 days by mid-1943. The United States was launching 3 Liberty ships daily, more tonnage than German submarines could sink. The workforce transformation was equally revolutionary. At peak production in 1944, Kaiser's 7 yards employed approximately 196,000 workers. Of these, over 40,000 were women. Women comprised 27% of Richmond's production workforce by mid-1944. African American workers numbered in the tens of thousands, employed in skilled positions, including welding, fitting, crane operation, and even supervisory roles. The democratization of skilled work that welding enabled carried implications far beyond wartime production. By proving that complex manufacturing could be performed by trained workers rather than requiring generational craft expertise, Kaiser's shipyards challenged fundamental assumptions about labor, skill, and industrial organization. The welding technique that British Admiralty had forbidden, that Lloyd's of London had questioned, that traditional shipbuilders had dismissed as inappropriate for maritime construction, had become the standard method for building cargo ships worldwide. The forbidden had become foundational. By mid-1944, Kaiser's 7 shipyards had produced over 800 Liberty ships, but the influence of welded construction extended far beyond his facilities. The 18 American shipyards building Liberty ships had collectively produced 2,400 vessels by this point. The total American maritime production between 1941 and 1945 exceeded 5,500 vessels, representing approximately 53 million tons of shipping. Each Liberty ship displaced 14,245 tons, fully loaded, and could carry 10,800 tons of cargo. The vessels could transport 2,840 jeeps, 440 tanks, or 230 million rounds of ammunition in a single voyage. The mathematics of supply were overwhelming. One Liberty ship every day meant capabilities arriving in Europe and the Pacific faster than Axis forces could counter them. Commander Joseph Kenworthy of the Royal Navy, assigned to the British Admiralty delegation in Washington, watched American production with admiration, captured in official reports declassified decades later. The United States is building merchant shipping at a rate that exceeds the combined capacity of the rest of the world. Kaiser alone produces more tonnage monthly than the entire British shipbuilding industry. The approaches are crude by Admiralty standards. The ships are inelegant, but they float, they carry cargo, and there are thousands of them. The Royal Navy built the finest warships in the world, using traditional craftsmanship, requiring years per vessel. The Americans build adequate ships in weeks. Adequate multiplied by thousands defeats perfection multiplied by dozens. The battle casualty rates among Liberty ships demonstrated their effectiveness despite skepticism about rapid welded construction. Of 2,710 Liberty ships built, approximately 200 were lost to enemy action, a loss rate of 7.4%. This compared favorably with pre-war merchant shipping loss rates. The structural failures due to brittle fracture, while dramatic, affected relatively few ships. 3 Liberty ships broke completely in half, representing 0.1% of production. Nearly 1,500 instances of significant brittle fractures occurred across the Liberty fleet, but catastrophic complete breaks were rare. These failures led to improved welding procedures and steel specifications that eliminated the problem by 1944. Longevity statistics provided ultimate vindication of welded construction. Liberty ships, designed as emergency vessels with expected service lives of 5 years, proved remarkably durable. Many remained in service for decades. The SS John W. Brown, built in 1942, remains operational as a museum ship in Baltimore in 2025, 83 years after construction. The SS Jeremiah O'Brien, also built in 1942, is preserved in San Francisco and participated in the 50th anniversary commemoration of D-Day in 1994, actually sailing to Normandy under its own power. Of the approximately 2,510 Liberty ships that survived the war, approximately 835 remained in commercial service through the 1960s. Many were sold to foreign shipping companies where they operated into the 1970s. The forbidden welding technique that maritime authorities had opposed in 1940 was still keeping ships operational 3 decades later. The technological innovations developed during the Liberty ship program influenced industries far beyond maritime construction. The welding techniques refined under wartime pressure became standard in structural steel construction, petroleum refining equipment fabrication, and pressure vessel manufacturing. The prefabrication approaches pioneered at Richmond influenced construction practices in housing, bridge building, and industrial facilities. Professor Michael Porter at Harvard Business School, analyzing American industrial competitiveness in a 1985 study, identified the Liberty ship program as a crucial case study. Kaiser demonstrated that industrial capacity is not fixed, but can be created quickly when necessity demands it. The United States entered World War II with minimal merchant shipbuilding capability. Within 24 months, American yards were producing more tonnage than the rest of the world combined. This proved that industrial infrastructure, workforce skills, and production systems could all be developed at unprecedented speed when properly organized. The welding revolution that made this possible began with a technique that traditional authorities had forbidden. Electric arc welding violated centuries of maritime practice. It lacked the proven track record that conservative engineers demanded. It introduced risks that riveting avoided. Yet when German U-boats were sinking Allied shipping faster than traditional methods could replace it, the forbidden technique became necessary. Kaiser's genius was recognizing that pipeline welding experience translated to ship construction. Traditional shipbuilders saw fundamental differences between pipelines and ships. Kaiser saw underlying similarities. Both were large steel structures assembled from components. Both required reliable joints. Both could be built using electric arc welding by trained workers following documented procedures. The resistance he encountered was predictable and rational. New technologies always face skepticism. Established industries always resist change. Authorities always demand proof before abandoning proven methods. What made Kaiser's achievement remarkable was not that he faced opposition, but that he overcame it through demonstration rather than argument. The SS, Robert E. Peary, built in less than 5 days, provided proof that silenced critics. The technique worked. The ships floated. The welds held. The workers, trained in weeks rather than years, produced vessels that served reliably for decades. Traditional wisdom wasn't wisdom at all. It was an accumulated assumption that had never been properly tested. The story of how one forbidden welding process made Liberty ships appear in days instead of months is ultimately about the difference between craft and industry. Craft relies on masters who possess comprehensive knowledge developed through years of experience. Industry relies on systems where specialized workers execute documented procedures. Craft produces excellence. Industry produces scale. In peacetime, excellence matters more than scale. In wartime, scale becomes survival. The Allies didn't win World War II because they built better ships than the Axis powers. They won because they built more ships, enough more that losses became acceptable, enough more that supply lines stayed open, enough more that amphibious invasions could be staged across multiple theaters simultaneously. The forbidden welding technique that made this production possible transformed not just shipbuilding, but fundamental understanding of manufacturing capability. Industries that had operated on craft principles for centuries discovered that industrial methods could produce adequate results at revolutionary scale. This lesson extended far beyond World War II. When Japan and South Korea rebuilt their maritime industries in the 1950s and 60s, they studied Kaiser's Liberty ship program and adopted welded prefabrication as foundational practice. The massive shipbuilding facilities in Ulsan, South Korea, and Nagasaki, Japan, that would dominate world shipping construction for decades, were direct descendants of Richmond Yard's revolutionary practices. Modern container ships, oil tankers, and cruise vessels are all built using approaches derived from Kaiser's Liberty ship program. Modular construction, welded assembly, prefabrication of major components, parallel production of ship sections. Every technique that traditional shipbuilders opposed in 1940 became a universal standard by 1960. The magnitude of transformation can be measured in statistics. 2,710 Liberty ships built across 18 American yards between 1941 and 1945, average of 1.8 ships per day at peak production. Construction time fell from 230 days to 42 days in just 2 years. Worker hours declined from 1.1 million per ship to 350,000 per ship through learning and optimization. Each Liberty ship required approximately 50 miles of welding. 2,700 ships meant 135,000 miles of electric arc welding, performed mostly by workers who had learned the skill just weeks before. The technique that authorities had forbidden as unsuitable for maritime construction had joined more steel than had been welded in all previous maritime history combined. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The Liberty ships are mostly gone now, scrapped decades ago, or resting on ocean floors, but the revolution they represented endures in every modern shipyard, in every manufacturing facility that uses welded construction, in every training program that teaches specific skills quickly rather than comprehensive expertise slowly, and in every engineer who questions whether impossible truly means impossible or simply means not yet attempted. Henry Kaiser's enduring legacy is carved not in steel, but in transformed understanding of industrial possibility. From December 1940, when he signed his first ship contract, knowing nothing about maritime construction, to November 1942, when the Robert E. Peary launched after less than 5 days of work, to September 1945, when the last Liberty ship was delivered, Kaiser proved that industrial revolutions happen through fundamental reimagining of what is possible. The 2,710 Liberty ships carried more than cargo across oceans. They carried proof that techniques dismissed by experts could revolutionize industries. That training measured in weeks could replace apprenticeships measured in years. That industrial methods could solve problems that craft traditions couldn't scale to meet. That the forbidden could become foundational when necessity demanded innovation and demonstration proved possibility. The welder who strikes an arc today, joining steel with electricity in seconds, participates in a revolution that began when traditional maritime authorities declared the technique unsuitable for proper ships. That revolution proved experts wrong, tradition insufficient, and impossible merely difficult. It remains the most important lesson of the Liberty ship program, not the ships themselves, but what their construction demonstrated about human capability when freed from constraint and challenged to accomplish what authorities claim cannot be done.